is lecture 5. And we'll be dealing with geodesics of connection and exponential map. So before I give you some results about the study of geodesics of a connection, let me remind you some of basic results about differential equations on manifold. So as usual, if you consider a manifold M, this is convenient to solve problems or for modeling to be able to define the notion of differential equation on the manifold. So the basic example of a differential equation is the example of the flow of a vector field. So consider the following problem, which will be to find a curve, smooth curve C on the manifold that satisfy the following property. So X will be a given vector field on the manifold, and we want to find a smooth curve C so that C prime is equal to X of Ct, and we have a given initial condition which is given by C of 0 is equal to X naught, where X naught is any point, in the manifold, and X is a vector field. So this is what we call a first order differential equation on M. This is an example of autonomous first order equation. So this can always be solved, at least locally. And this yields the notion of exponential of vector field. So there exists always a local solution to this equation, which is defined on some maximal open interval. That contains 0. Okay, so this is very easy to see. This is just Cauchy-Lipschitz existence theorem for first order differential equation. I mean, you can rewrite the equation C prime t is equal to X of Ct as being a first order differential equation written in a chart. Then you apply the usual theorem about existence and uniqueness for solution of differential equations in Rn. Okay, so you can translate the problem into Rn, and you'll see that always there exists a unique solution of this equation, which is going to be defined on some maximal interval. Does it make sense to everyone? So let me know if you're still having problem with the sound. It seems that on my side the connection is not completely stable. So the solution of this equation x prime, the solution of the equation C prime is equal to X of Ct yields the notion of exponential of vector field. So we write Ct is equal to exponential of tx of x naught. So this is the definition of exponential of vector field. Yeah, we're still having problem with the sound. That is, there is still some noise, some background noise. And the connection is not very stable today. Okay? So, more generally, so this type of equation is the simplest kind of equation. These are first order equation driven by a vector field. Note that the solution might not be defined globally. That is, it's possible that the solution blows up, so that the maximal interval I is not equal to R. Okay, if I is equal to R, then we say that the vector field is complete. Okay, so an example, of complete vector fields, for instance, if you have a compact manifold, any vector field is complete. Because the solution, C, cannot blow up. Okay, because the manifold is compact, so the solution C itself cannot blow up. So if M is compact manifold, then any vector field on M is complete. Okay. Very good. There is another kind of differential equation which is very useful, especially in so-called geometric control theory. This is the notion of controlled ordinary differential equation. So assume that you are given n functions, or going from an interval I into R, which are smooth, as usual. We can consider the following ODE. C prime t is equal to the sum for I is 1 to n of the gamma it xi of ct, where the xi, as before, are smooth vector fields on the manifold. This is what we call a controlled ordinary differential equation, and the functions gamma 1 up to gamma n are called the controls of the equation. Okay, that is gamma 1 are called controls. So these are known. That is, you assume in this point of view that gamma 1 up to gamma n are known functions, and what you want to find is a curve C on the manifold. So this is a non-autonomous differential equation. But the theory of existence and uniqueness applies as well, I mean, you can just look at the equation written in a local chart, and you apply existence and uniqueness results, for first order differential equation in AN. So there exist, again, provided that you have an initial condition, C of 0, which is equal to x0. So there exists a solution unique, defined on a maximal interval around 0. Okay, so these are the two types of equations that we'll be going to see, and these are the two types of first order equations that appear naturally in geometry. So let me give you a basic example of an equation which is going to be an order 2 equation, which is the equation of geodesics. So geodesics are defined with respect to a connection. Keep in mind that at this point of the course, I did not speak of any kind of Riemannian structures yet. That is, the notion of geodesic I'm going to define now is really relative to a connection. So if you have a connection on a manifold M, definition, so we say that a curve C is a geodesic So the curve C can be defined on any kind of open interval into the manifold. So I should precise, we call this a nabla geodesic. That is, this is a geodesic relative to the connection nabla. But you'll see that in the sequel, I will drop, the terminology nabla geodesic because there will be no confusion for the connection I'm working with. If the following equation is satisfied, you want essentially that the covariant derivative of C prime along C prime is equal to 0. Okay, so you need to understand what we explained last time. That is C prime, if you have a smooth curve C prime is a vector field which is defined only on the curve C itself. Okay, so the terminology nabla C prime of C prime means that you are differentiating a vector field which is defined only on the curve. But we explained what it means last time. It makes sense because if you differentiate with respect to C prime a vector field which is defined on C only, you only take derivative in the direction of the curve, which is something that you can compute, knowing only the value of the vector field on the curve. So this is the definition of geodesic. In some sense, you should see that as a generalization of curves whose acceleration is 0. Acceleration with respect to the connection nabla. So nabla C prime of C prime should be seen as a second derivative of C with respect to the connection nabla. So it's important to understand how does the equation of geodesic looks like, if you are using local charts. So consider a local chart U phi So this yields a trivialization of the tangent bundle. And for this trivialization, I have the trivial connection, nabla 0. So as usual, we can write nabla as nabla 0 plus gamma, where gamma is the Christoffel tensor of the connection nabla. We can write a local frame of vector fields with respect to this trivialization. So the vector fields x1 up to xn, by definition, they are parallel for the trivial connection. And using this frame, we can write the equation for geodesics as follows, using the Christoffel tensor. So we look for a solution, that is, we look for a solution of the geodesic equation somehow as a controlled ordinary differential equation. So we look for, but in this controlled ordinary differential equation, the controls can be computed exactly in terms of C, because note that the coefficient Ci prime can be computed in terms of C only as a dual with respect to the frame xi of C prime. Okay? So we are going to see conditions on the Ci so that C is a geodesic. Okay, that is, we solve the differential equation nabla C prime is equal to 0 in the frame xi. Okay, so the unknown of this problem are the function Ci. If the Ci are known, then C will be known. Does it make sense to you? So there are two levels for solving this problem. We are going to write an equation for the Ci's, and then once we know the Ci, we'll be able to obtain C. So if I write the equation nabla C prime is equal to 0, I can write it in this frame xi. This is equivalent to the fact that nabla of the sum of the Ci prime xi, Ci prime xi is equal to 0. Okay? So you'll see that if you differentiate the function Ci with respect to the sum of the Ci prime xi, the only derivative which is going to survive is the second derivative of Ci. So the first term, when you use the tensorial property of the covariant derivatives, is the sum of the second derivative of Ci xi, computed at the point Ct. And then you have the covariant derivatives of, so maybe I will write more steps, because I want to show you all the steps. So I will add one more step in the computation. So the step I want to show you is the step where we use a trivial connection. And then you have the Christoffel tensor, which is a sum over ij of ci prime t cj prime t of gamma of xi xj, computed at the point ct. Okay, so if you write the geodesic equation in the frame xi, you end up with this equation. The first term of the equation simplifies because you know that the frame xi is parallel for the trivial connection nabla 0. So the only derivative which is going to survive is the second derivative of ci, which yields the term second derivative of ci xi of ct. All the other terms will be 0 due to the fact that the frame xi is parallel for the trivial connection. And the second term is unchanged. You get the sum over ij of ci prime t cj prime t gamma of xi. So I should use xj of ct is equal to 0. Okay? So the final step, to be able to write a system on the ci is to decompose gamma xi xj, which is a vector field. So it can be decomposed in the basis xk. And if I decompose gamma xi xj in the basis xk using the following notation, okay, so this is a notation for the Christoffel symbol of the tensor gamma in the frame xi. So denoting this, we obtain the following equation. That for all k, the second derivative of ck plus the sum over ij of the gamma ijk of ci prime cj prime is equal to 0. So this is a geodesic equation written in the local frame. Okay, so in this notation, the gamma ijk are the so-called Christoffel symbols, which are defined as being the component of the Christoffel tensor in the basis xk. Does it make sense to you? So you observe that the geodesic equation is not a linear equation. Okay, so this is not. So instead of in the chart here, I should write in the frame xi. So this is not a linear equation. So this is a second order, nonlinear differential equation. Okay, but the local theory of ordinary differential equation still applies, even to nonlinear equation, and always you are able to solve locally the geodesic equation. Okay, that is, if you work on a small time interval, this is always to find locally a solution of this system of equation. So once you find the CI solving this equation, if you go back to the definition of the CI, you'll be able to find C. Using the formula, C prime is the sum of the Ci prime xi. You use the Ci as controlled. So the C itself, is obtained by solving a controlled ordinary differential equation. Does it make sense to you? Okay, so an example is, for instance, for the trivial connection itself. We may wonder what are, the geodesic. So in that case, for the trivial connection itself, the Christoffel symbols are 0. So in that case, the geodesic equation simplify. And what we get is that the second derivative of the coefficient ck in the frame xi are equal to 0. Okay? So this means that the ck are straight lines. Okay, so somehow, for the trivial connection, the geodesics are straight lines. So if you come back to the definition of C, you see that Ct is equal to the sum over I of AI x of Ct. Okay? Where the AI are constant. So this means that Ct is the exponential of some vector field. Okay? So this is the characterization of geodesics, for a trivial connection. They are characterized as the exponential of a vector field constructed from the connection. That is, the xi, I remind you, are parallel for the connection nabla. Does it make sense to you? So the components are straight lines, and the geodesic itself is the exponential of a vector field. So this characterization of geodesics, for the trivial connection yields to a notion of exponential map. That is, we would like, in some sense, to introduce an exponential map associated with any connection. You just see from this computation that if you use a trivial connection, you recover the exponential of vector field that I introduced at the beginning of the class. But now if I use a general connection, which is not a trivial one, that is for which the Christoffel tensor is not 0, then we get a new notion of exponential map, which is very important. So the next step for us will be to introduce the exponential map associated with the connection. So let me write a little bit explicitly what I told you a few minutes before, is that from general existence theorem, this is also the occasion to introduce some notations. So from general existence theorem for solutions of ODEs, even nonlinear ODEs, given a point x in M and a tangent vector x at the point x, okay? Since the geodesic equation is a second order differential equation, we can find a unique solution geodesic that I'm going to denote by Cx just in this course, which is defined on a maximal interval around 0 that satisfies that the value at 0 of Cx is equal to x, meaning that the geodesic starts at the point x, and the initial velocity of the geodesic is given by the vector x. Okay, so there exists a unique geodesic which is given initial condition. This is only because the geodesic equation is a second order equation. So if you fix the initial position and the initial velocity, locally you have a unique solution which is defined on a maximal interval I. That is, I is the largest interval on which you have uniqueness and existence. This is called a maximal interval of definition. Okay, so now let's introduce some notation for the set which will turn out to be the so-called domain of the exponential map. That is 4 notations. For x in M, we are going to denote by dx the set of vectors at x, that is the set of vectors in the tangent space at x, such that 1 is in I. That is, 1 is in the interval on which is defined Cx. So what does this mean? It just means that you want to make sure, and 1 is a convention. I will explain this a little later. You could pick any positive number. It's just going to yield a rescaling of the exponential map. So we choose this number 1 only because this is positive, and to fix what we call a unit speed. So what does this mean, dx? It means that you have a vector x, big X at the point X. You solve the geodesic equation in the direction of big X, and if you are able to solve it up to time 1, then you say that his x is in dx. Okay? And number 2, you may observe that dx is an open set, is in the inside of the tangent space. This is due to the continuity of solutions of differential equations with respect to the initial condition. So dx is open inside of the tangent space. Then you introduce a bundle, which is D, which is a union of all the dx. We are going to get something which is open inside of the tangent bundle, because you have a union of open sets. So D is called the domain of the exponential map. Again, keep in mind that this exponential is relative to the connection we are dealing with. If you change the connection, you change the geodesic equation, and as a consequence, you change the exponential map that I'm going to define. Okay? So it's a slight abuse of notation only to speak about exponential map. If I want to be very precise, I should say exponential map relative, to the connection nabla. So then, the definition of the exponential map itself is simply by the value of the geodesic at the time 1. So the exponential map of nabla, of the connection nabla, is a map which is defined on D that takes value inside of the manifold, and this is defined by the exponential of x, that is, if you have a vector field in D, then this is the value of the geodesic at time 1, which is started in the direction of big X. Okay? So this is usual to denote exponential based at X, the restriction of the exponential map to dx. Okay, so exponential based at x is a map that acts on the tangent space at x. So this map is obtained by solving the geodesic equation in the direction of big X up to time 1. Okay? Does it make sense to you? So this exponential map is not to be confused with the exponential of a vector field. Okay? This exponential map defined using a connection will be the same as the exponential of a vector field only if the connection is trivial. This is the example I have shown you before. If the connection is not a trivial connection, then this exponential map defined by the connection is not the exponential of a vector field. Okay? So be very careful with that. The exponential relative to a connection cannot be written as the exponential of some vector field. This is simply not true. So there is an important fact which is used to define what we call exponential coordinates, is that the exponential map is going to induce a local diffeomorphism between a neighborhood of the tangent space at x and a neighborhood of the point x inside of the manifold. That is, the exponential map defined using the connection nabla will define a set of coordinates around any point. Those coordinates will be called exponential coordinates. So this fact is based on the property that the differential map, that is the differential of x of this map, which is a map between the tangent space at x and the neighborhood of the point x at 0, okay, is the identity. That is the identity of the tangent space Txm. For any connection, when you differentiate at 0 the exponential map, what you get is the identity map. So this is not difficult. Using the definitions of the geodesics. Okay, so this is based on the fact that I'm just going to give a sketch and let you fill in the details. So this is based on the fact that the geodesic equation is homogeneous equation. Okay, so as a consequence of that, it's not difficult to see that if you rescale a vector x by a parameter epsilon, this is the same as rescaling the geodesic that is started in the direction of x, and you rescale it in time. Okay, so this is going to be true for any epsilon, which is a rescaling parameter. Provided, of course, that epsilon is small enough so that the geodesics are well defined on the time intervals we consider. So if you look at this relation property, differentiating Cx at 1 with respect to x this is the same as differentiating Cx with respect to epsilon, that is with respect to time. As a consequence, the derivative of Cx of 1, with respect to x itself, is simply a time derivative of Cx with respect to epsilon. And at a point 0, C prime of x of 0, by definition, is x. Okay? Therefore, the derivative of Cx in the direction of x at 0, that is, if you differentiate at the point 0 Cx, you compute this as 0, this is equal to x. Okay? So therefore you have the identity map, because this is the directional derivative of the exponential map in the direction of x. Is everybody with me? So everything is okay with the sound for everyone? Okay. So if I don't hear anything, I presume this is okay. Okay, and also if I don't see any comment in the chat, so I presume that you are still listening to me. Okay. So let's come back now from this theorem to what I was telling you about the exponential chart. That is, from this theorem, we know that the derivative of the exponential map at 0 is the identity. So this means, from the implicit function theorem, there exists a neighborhood of 0 in the tangent space at x. Okay. And the neighborhood Vx of x in M such that the restriction map of the exponential map is a diffeomorphism onto Vx. Okay? So Txm is a vector space. Therefore, this is a definition of a local chart. So such diffeomorphism yields a local chart called exponential coordinates. So exponential coordinates are quite useful as the preferred choice of coordinates when you have a connection. Okay, because we'll see later that the curvature tensors compute relatively well in exponential coordinates. That is, if you work in exponential coordinates, a lot of complicated tensors, they take simple expressions. We'll see that specifically in the case of Riemannian or pseudo-Riemannian manifolds. Okay? So remark. The remark is that a connection nabla is called complete the domain of the exponential map is the tangent bundle itself. This is the case, for instance, on a compact manifold. That is, any connection on a compact manifold is complete. This is simply because in that case, geodesics, they cannot blow up. Okay, that is, they are defined always for all times. So example, so let me give you two examples. So for instance, Rn with a trivial connection is complete. By the way, to make sure you're with me, so in that example, that is in that trivial example of Rn with a trivial connection, what is the exponential map? Can someone tell me what is the exponential map? That is, if I try to compute, you know, the exponential map for the trivial connection in Rn. So in that case, what is the formula? Does someone know what is the formula for the... So it seems that we got disconnected. Does it work now? Can you hear me? Is the connection better now? Can everybody hear me? Yes, that's okay. Gianmarco, can you hear me? Okay, good. So everybody else can, I presume. Okay. So to make you participate a little, I was asking you what is the exponential map in the case of Rn with a trivial connection. Anybody can answer. That is not necessarily Gianmarco. That is, we have seen, and this is one of the examples I gave, that for the trivial connection, the geodesics are straight lines. So having this in mind, what will be the exponential map? That's a pity. I cannot hear you very well. I think Liang Bin was speaking. What did you say? Yeah, the sound is too bad today. So maybe you said it was translation because this was the answer I was looking for. So the answer is simply the translation. Okay, that is the exponential map for the trivial connection in Rn is the translation. Second example of connections which are always complete are the case of compact manifold. That is, if M is compact, any connection is complete. Okay. There is a last example that I'm just going to mention orally. That is, I will not write it because this is something I will develop further later. This is a case of Lie groups. That is, if you have a Lie group with a left invariant Riemannian metric, it turns out that the exponential map associated with the Levi-Civita connection of this Lie group is exactly the exponential map from the Lie algebra to the Lie group. Okay, so this is an example I want to study a little bit deeper later, so I don't speak too much about it now. This is just to tell you that the notation exponential and the notation exp for C is exponential related to a connection is very well motivated because it coincides, you know, what is the exponential in the groups. Okay, so now we have seen how to compute the derivative of the exponential map at 0. It turns out that this is possible to compute the derivative of the exponential map at any point, that is at any vector in Txm. This relies on the notion of Jacobi field. So this is a very important notion that I want to present now. Is the notion of Jacobi field. That is, consider a connection nabla, as before, and a geodesic for this connection C. The Jacobi field along gamma, along C, are vector fields which are defined only on C and that satisfy a special second order differential equation. So a Jacobi field J along C is a vector field defined on C So it's a vector field defined on C that satisfies the following second order differential equation. So the equation is nabla C prime of J. So this is the second order covariant derivative along the curve plus the curvature tensor of the connection nabla taken at C prime J C prime plus the covariant derivative in the direction of the torsion C prime of J is equal to 0. Okay, where R, that is, as always in this course, is the curvature tensor of the connection nabla. And T, it's torsion tensor. So why are Jacobi fields a fundamental object, defined along the geodesic? This is because of the following theorem. The theorem is that you can compute the derivative of the exponential map at other points than 0 by computing Jacobi fields. So this is a very important theorem, is that for y, which is at the tangent space at x, and x, which is in dx, that is in the domain of the exponential map at x, the derivative, the differential of the exponential map in the direction of x at the vector y is the value at the endpoint of the geodesic. That is, this is the value at Cx1 of the unique Jacobi field along Cx with initial data so the Jacobi field at 0 is 0, and the first derivative of J along C prime at the point 0 is y. Okay?
Professor?
Yes?
Before, when you wrote dx exponential the point x, y,
yes,
are the fields x and y switched?
That is, you compute the derivative in the direction of x, big X. So this is my notation here. That is, you should see that like this. I don't know if this is clearer like that. So it means that I do a variation. So before I turn to the proof, maybe I will explain a little bit the notation. What I do is something like this. I have x, and I do a perturbation in the direction of y. Okay? So C's first order expansion is exponential x, that is at first order, plus epsilon dx, that is you compute at x, you know, the derivative of the exponential map in the direction of y.
Okay, that's fine.
Yes, okay, so this is C's notation. So what does it mean? Let me try to make a picture to explain this theorem. That is, you have a point x and an initial velocity x. What you do is you solve in the manifold the geodesic equation up to cx of 1, which is by definition the exponential at the point x of big X. And you wonder what happens if instead of starting at big X, you do a small perturbation of big X. So I will use another picture, another color to do that. This is a good thing with the iPad. Oh, but it's too large. This one should be better. So here you should imagine that you have x plus epsilon y, and that epsilon is very small. That is in my picture, you know, they are far away, but you should imagine that epsilon is very small. So in that case, you solve the geodesic equation associated with C's initial velocity. So the endpoint is going to be exponential x of x plus epsilon y. Okay. And the question about the Jacobi field, that is the theorem tells you that the Jacobi field, J, I will put it in red, is a vector which is there. Okay. That is the theorem tells you that the two geodesics, you know, how they end up far away depends on the Jacobi field at C of x1. That is, C's vector in green is J of C of x1. Okay? So if you want to compute the perturbation of a geodesic Cx, you know, when you change the initial velocity, you need to compute the Jacobi field. Computing the Jacobi field is solving a second order differential equation. Okay, so I come back to so this is the theorem I will prove next time, because I don't have the time to prove it now, but I will give you the proof for the computation of the derivative of the exponential map of a connection. But before we give the proof next time, I want to come back to the definition of the Jacobi field. So Jacobi field is obtained by solving a second order differential equation along the geodesic gamma. Okay, so next time, that is on Tuesday, I will show you how does the Jacobi equation look like, you know, when you write it in a local frame. And then I will give you the proof of this theorem. Does it sound good to you? So again, and this reflects what I was telling you before, that always you can compute all geometric quantities using the curvature R and the torsion T. Okay, this is a general fact in geometry. The two defining tensors of any connections are the curvature tensor and the torsion tensor. Any other relevant tensor can be written only in terms of these two tensors. Do you have some questions? Try to think about this picture, you know. for next time. I think that's a nice picture to think about. That is, this is how the geodesics can be perturbed, using Jacobi fields. So do you have some questions?
I do like a very quick question.
Yes.
So far, it's not clear whether the Jacobi fields exist or not, right? Because
exactly.
I just want to point out. So maybe in the proof of the theorem, we'll see.
Exactly. So that's a very good question, actually, Marco. Is that at this point we don't even know if they exist or not.
Okay.
Yes. So this is something I'm going to explain next time, because I will start next time by explaining you why is the Jacobi equation a second order differential equation. So we'll be writing explicitly this equation inside of a frame, and we'll see that we'll be able to solve it.
Okay. I was just double checking because so far it was not 100% clear to me why. No. I mean, I believe they exist because I believe the equation is solvable, but
the equation is solvable simply because this is actually a linear equation.
Oh, okay.
It's a second order linear equation.
Okay.
So this is different from the geodesic equation, which is not a linear equation. This equation for the Jacobi fields, we'll see that this is a linear equation.
Oh, I see. Okay.
Yeah. So there is the whole theory of linear second order differential equations that we can use to obtain actually global solvability, along the geodesic for the Jacobi field. Okay.
Yeah. Thank you.
Okay, no problem. Are there any other questions?
Hello, Professor. I have a question about the controlled ODEs in the beginning of the lecture.
Yes.
So you were talking about some given functions, smooth functions from gamma 1 to gamma n.
Yes.
And should the n be the dimension of
okay, so that's a good point. It does not need to be. Okay, that is, it could be more general than that. You could consider, I will change maybe the notation because I am given the chance now. You can put m here instead of n. That is, it can be any number. Okay?
Okay, got it, thanks.
Yeah, no problem. And the xi do not need to be independent, neither for the definition of the controlled ODE. That is, you can consider any vector field. The last point, yes, okay. And the last point related to controlled ODE is that the solution is not the exponential of a vector field. Okay, that is, there is a formula, which is a very complicated formula, which is called the chain formula, that expresses the solution of controlled ODEs, but this is not a vector field. It involves the Lie bracket, of the xi at any order. So it's a complicated object.
Okay, thank you very much.
Okay, no problem. Any other questions? Okay, so if not, I remind you that the exercises 1 and 2 are due today. Okay, so I'm waiting for them. I sent you yesterday next exercise, which will be exercise 3, which is due in 2 weeks. And I will send in the next few days exercise 4, which is also going to be due in 2 weeks. Okay, so I apologize for the technical difficulties. It seems that there was too much traffic on WebEx, but I hope that the sound was reasonable, for everyone, and that we were able to see the iPad correctly. So I wish everyone a good weekend, and as usual, you'll be able to see the lecture, the video of the lecture on my webpage later today. Okay, so have a good day. Bye-bye.